hydrogen stretching. Problem is it's superimposed on the alcohol that's there as well.
So it says between 25 and 4,500. What would carbon go above like 3,000?
There are things that, like ring structures and other things that are attached to it that can cause it to go outside that range. It's rare when it gets much higher than that.
But your CH stretch is still below 3,000 unless there's
Yes.
double bonds in the
Yeah, the regular carbon hydrogen stretch is still below 3,000, or if there's double bonds, they'll be above 3,000. The problem is that they'll be superimposed on this broad, ugly band here, the OH of the carboxylic acid gives you. And again, it's farther down in energy because these bonds have been further weakened by extra hydrogen bonds. Okay, and broader than usual as well. Some variations in the carbonyl band, normally around a little over 1,700, but if it's conjugated with a double bond, carbon-carbon double bond, because of resonance, this pair of electrons can come out here to move the double bond here. This double bonding pair of electrons can go out on the oxygen, and you create an alternate resonance form. Which of those two resonance forms would you expect to be more important? One on the left and one on the right? One on the left. Remember, one of our rules for resonance.
Or a form of chart? No. At least I'm trying. Bring it on.
They're both, one on the right, for one thing, the carbon doesn't have an octet.
Right.
And nature doesn't like the formation of charge.
No.
But nevertheless, there's enough experimental evidence to indicate that there is some content like that as part of the resonance structure. And because of that stability associated with that, that tends to weaken this double bond or make it more stable. So we see it shifting to lower wave numbers. So for an isolated carbonyl, we'll expect it up around 1720, 1715, 1725. Notice that by conjugating it with a carbon-carbon double bond, it falls well below 1600. Okay? Now, amides. You aren't given an amide structure here, so let me draw an amide for you. Here's our carbonyl band. If I have a carboxylic acid, I have an OH out here, but an amide has that. Okay, this is what we call an amide in organic chemistry. And notice that this nitrogen group here, these hydrogens can either be hydrogens or carbons, so I can have substituted amides as well. Okay, and in fact, in proteins where I've got peptide bonds, they will be. Okay, this, by the way, this is the bond, the amide bond, that's associated with peptide. It's a peptide bond. It's in fact an amide bond. And so we see these things fairly commonly in chemistry. Notice that this guy has the carbonyl stretch, and it's got something unique out here instead. Look what it does to the spectrum. These are usually fairly easy to see. Notice that the carbonyl band goes pretty low. Whoops. Goes pretty low here. And out here I see evidence of the hydrogens on the nitrogen. So the amide structure is fairly easy to diagnose as well. Now I know we're just sort of cataloging information for you. I know that you've not done enough IR to feel comfortable with this yet, but over time, in investing some study in terms of problem sets and so forth, you'll actually be fairly comfortable with this stuff. And some of you probably already are a little bit, have a feel for this already. The infrared, and we'll get to this here in a moment, is largely valuable for diagnosing major groups, cataloging and categorizing your unknown compound in a certain general area. Very rarely can you take an IR and say, oh, this is such and such a compound. There are IR spectroscopists that can, but they're professionals and they do this for a living. That's not like the rest of us here. And so we use this technique to say, I would look at this and say, I have an amide, or an amide, I wouldn't know that this particular amide has 3 carbons attached to the amide functional group. That would have to come from other information. Now, we talked about carbon-carbon stretching a while ago. Look at carbon-nitrogen. Interestingly enough, bond energies are very similar. So carbon-nitrogen is at about 1,200 centimeters, just like carbon-carbon. Same with the carbon-nitrogen double bond and the carbon-nitrogen triple bond, but these bands are much stronger. Why? Polarity. These are more polar than the carbon-carbon variety, and so these usually appearing in the same region, but they're usually more intense, which helps us identify them, or I suggest the possibility. Here is a cyano group, or nitrile, carbon-nitrogen triple bond, and we see it in the same region that we see the carbon-carbon triple bond, but notice that the peak is more intense. Remember the carbon-carbon triple bond was maybe only about half that. You remember that, right? We saw that a few minutes ago. This one's a lot more intense. Summary. Just some general regions where we expect to see the different bands. Nitrogen, hydrogen, oxygen, hydrogen, or carbon, hydrogen, as well as the multiple bonds, as well as the basic single bonds which appear in the fingerprint region. In general, when I'm doing a spectral problem, the first thing I'll do is I'll look at the IR. And I'll just look at it in a very descriptive fashion, just to see what bands are present. An intense band right down here would be what?
We have carbon.
Probably that guy. Which would be more polar, that guy or that guy?
Those are 2.
Carbonyl. So a band around 1700 is the deepest, most intense band in the structure, almost always a dead giveaway for a carbon-oxygen double bond. And there are some pretty regular, predictable things that you can hang your hat on in the IR spectrum. And the better you get at it, the more you look at some of the subtleties. But this region, from about 14 to 1500 and out, is where you'll start to look for important features in the IR structure. Generally, we don't go much further than that. Other spectroscopic techniques will allow us further insight, coupled with our IR information, to make that prediction not be identical. There's a little more detailed table about kinds of things that we might see in the diagnostic region of the IR. Not the fingerprint region, but the diagnostic region. On a test, I'll always give you data that will be sufficient to figure things out. Should I give you a date for that? How are you doing? Here's a problem, and the peaks are not labeled in terms of their wavelength. We look at this, let's look at this as a fresh problem for us to consider. Notice what do you notice right off the bat?
That big, strong carbon.
Yeah, not nitrogen, but carbon oxygen. Yeah, notice down here, it looks like, oh, here's 1700. So it looks like maybe around 1725, a big, intense band, most intense band in the spectrum. And we see its little overtone up here, which we've seen before. It's not an alcohol, it's an overtone of the intense carbonyl. So we know, based on the structures we've seen, we can narrow it down to either ketone, aldehyde, carboxylic acid, or an amide. We know that there are other features we can look for to identify those things. So, we don't see the big, broad band here associated with the carboxylic acid. And we don't see anything out here that suggests an amide. Remember that the nitrogens, or the hydrogens on the nitrogen of an amide are out there, look very much like an amine, and we don't see any evidence of that. So we're down at this point to either a ketone or an aldehyde. True?
Yeah.
So what do? I look, here's 2500. Here's 2600, here's 2700. Just above 2700 I have a peak. Just above 2800 I have a peak. What does that suggest to us? Suggests an aldehyde. And notice that all of the main hydrogen stretches are below 3,000, so what does that tell us?
Okay.
Yeah, no carbon-carbon double bonds. I've got a saturated aldehyde, as it were. Does that make sense? That's pretty much all you can get out of the IR. Now, let's suppose you've got some NMR data, and you say, I think this is, coconut, with 3 carbon aldehyde. Then what you could do is you could look up the infrared spectrum for coconut and compare it side by side with yours and see, although this is not very interesting right here, see if there's a peak-for-peak correspondence with an authentic spectrum. That's where you would use the finger poke. Does that make sense? And here's what we just went through. And ultimately come to the conclusion, because of these 2 peaks here, that we've got an aldehyde. Just as we do. Strengths and limitations. Infrared, by itself, as I indicated, rarely can be used to identify a compound. Some of the signals overlap. I've got carbon-carbon, carbon-nitrogen, bonds that overlap with one another. There isn't real clear cut. There are a few things that are pretty obvious, but very few. There can be some ambiguity. However, functional groups are usually identified with the infrared, and the absence of functional groups is identified. In other words, if I've got a big OH stretch, it says I got an alcohol. If there isn't a big OH stretch, what does it say?
It's not
You don't have an alcohol. And so this thing can, in fairly unambiguous fashion, eliminate or suggest the presence of important functional groups. All right? Again, in the end, once I think I've identified my compound, I compare the spectra side by side, particularly in the finger location. And that's really kind of how infrared is used in modern qualitative analysis. Now we look at a different technique, and we'll make mention of this occasionally in each chapter as we talk about the characteristics of different functional groups. Mass spectrometry is really the gold standard in identification. It turns out that mass spectrometry, coupled with a good library system, good data storage system, really pretty much unambiguous in identification. You'll take an unknown compound, inject it into a GCMS, that's a coupled gas chromatograph mass spec system. Those systems they'll analyze the sample and do a computerized report. They don't require any brains on your part at all, other than being able to stick a syringe in the instrument without jabbing yourself. And the computerized report will say it's 99.98% this compound, 0.24% it's this compound, and it's usually that clear cut. Now, there are possibilities for compounds to be similar enough in structure so that you'll have a reasonable probability of more than one thing, but almost always the mass spec is enough by itself to identify the compound. Problem is mass spectrometry is expensive. And we have one at the other campus that nobody uses. It takes a lot of maintenance and a lot of care to make it work properly. And so out here we'll do without, and you'll learn a little bit about the theory. And I could give you a mass spectrum, and we could probably make some suggestions for it, but we won't spend a lot of time on it because, by and large, the operator expertise in running mass spectrometry has been taken out of it. There's not an awful lot of theory and intellectual challenge associated with it. If you get the sample in there, you know what it is pretty much. It can be done with a very small amount of sample. It's actually done in a high vacuum system. And so small amounts are capable of giving you a good signal. In the technique, your sample is shattered or broken into fragments by a high energy beam of electrons as they pass into the electron beam. The sample is put on is destructive, right? It's destroyed. But the masses of the fragments and the relative amounts, or condenses,